The goal is to split a directed graph into its strongly connected components. That means partitioning the vertices into groups. Inside each group, from any vertex you can reach any other vertex in that same group by following directed edges forward. Picture a directed triangle, 1 points to 2, 2 points to 3, 3 points back to 1. Along the arrows you can walk from any of these three vertices to any other, so they form exactly one strongly connected component. Here 1 and 2 point to each other, so they can still reach each other both ways. Vertex 3 only points to itself for reachability inside its own group, and there is no way back from 3 to 1 or 2. So we get two strongly connected components, the pair 1 and 2, and the singleton 3. If the only arrow is from A to B, you cannot walk from B back to A. So A and B are not mutually reachable in both directions. Each vertex sits in its own strongly connected component. Later we will walk through Kosaraju's algorithm and Tarjan's algorithm to find strong components in linear time. The problem we solve is to split a directed graph into its strongly connected components, partition the vertices so each group is maximal and mutually reachable. Kosaraju's algorithm does that in 2 passes. First, run depth-first search on the original graph and record a stack order by finishing time. Second, reverse every edge, then run depth-first search again in that stack order. Our example has 4 vertices. 0, 1, and 2 form a directed cycle, and 2 also points to 3. There is no way back from 3 to the cycle, so we expect 2 strongly connected components. We assume you already know depth-first search on a directed graph. This scene does not teach DFS itself. Here we only show what to record for Kosaraju. Pass 1, explore with depth-first search on the original graph. When you are completely done with a vertex's outgoing exploration, push it onto a stack. Each push adds to the top of the stack. Vertex 3 finishes first, so it sits at the bottom. Then 2, then 1, then 0 on top. Later we pop from the top. Now build the transposed graph. Every arrow is flipped. An edge from A to B in G becomes an edge from B to A here. Pass 2, repeatedly pop from the top of the stack. Each time you pop an unvisited vertex, start a new depth-first search on the transposed graph. Everything reached in that search is one strongly connected component. Pop the top, 0. Run depth-first search on the transposed graph from 0. Pop 1, pop 2, both are already visited, so we skip starting a new search. Pop 3 last. Its search only finds itself, the second strongly connected component. The stack is empty. That is Kosaraju's method, 2 depth-first search passes, each touching each vertex and edge a constant number of times. Tarjan's algorithm finds strongly connected components in one depth-first search. This scene is in 2 parts. First we only learn how discovery and low-link values are set on a tiny graph. Then we run the full algorithm on the same 4-vertex example as Kosaraju, shown as a preview on the right. Part 1, we only watch discovery and low. Discovery number is the order DFS first enters each vertex. Low starts equal to discovery, then changes only in 2 ways, a back edge to a vertex still on the stack, or a value passed back from a child when recursion returns. Start at vertex 0. First visit, discovery is 1, and low starts at 1 as well. Move to vertex 1, discovery and low both become 2. Move to vertex 2, discovery and low both become 3. Relax the edge from 2 back to 0. 0 is already on the recursion stack, so this is a back edge. Update low of 2 to the minimum of its current low and the discovery number of 0, min of 3 and 1 is 1. Depth first search returns to vertex 1. After the child 2 finishes, merge, low of 1 becomes the minimum of its own low and the low reported from 2, min of 2 and 1 is 1. Return to vertex 0. Low of 0 becomes the minimum of its low and the low from 1, min of 1 and 1 stays 1. Those min updates are the only way low moves. Next we apply the same rules on the full graph with a stack and components. Part 2, same discovery and low rules as before, now on the full graph with a vertex stack. When low equals discovery at a vertex, we peel off one strongly connected component. Start depth first search at vertex 0. It is the first discovery, so disk and low are both 1. Push 0 onto the stack. New pushes go on top, same layout we used for Kosaraju. Follow the edge 0 to 1. Vertex 1 is discovered second, so disk and low both start at 2. Push 1 above 0. Edge 1 to 2, vertex 2 is discovered third, so disk and low both start at 3. Push 2 on top. Now relax the edge from 2 back to 0. Vertex 0 is already discovered and still on the stack, so this is a back edge. Set low of 2 to the smaller of its current low and the discovery number of 0, min of 3 and 1 is 1. Next, tree edge 2 to 3. This is the fourth discovery, so disk and low for vertex 3 are both 4. Push 3 on top. Here is the full stack with bottom and top labels, matching the Kosaraju scene. Vertex 3 has no unvisited outgoing edges. Its low equals its discovery number, so 3 is the root of a finished strongly connected component. Pop from the top of the stack until and including 3. Vertex 3 is its own strongly connected component. The stack still has 0, 1, and 2 from bottom to top. Depth first search continues by unwinding, we are back at vertex 2. At vertex 2, low is still 1, which does not equal discovery 3, so 2 is not a component root yet. When we return to vertex 1, low of 1 becomes the minimum of its discovery and the low reported from 2, so low of 1 becomes 1. After finishing 2 and 1, neither is a root yet, so we still do not pop a new component. When DFS finishes vertex 0, low of 0 equals discovery of 0 at 1. So 0 is the root of the last strongly connected component. Next we pop from the stack in order, 2, then 1, then 0. Those 3 vertices form the second strongly connected component, the directed cycle among 0, 1, and 2. That is Tarjan's method, one depth first search, low link numbers, and a stack to extract strongly connected components. Kosaraju's algorithm runs in order v plus e time, 2 depth first searches, each visiting every vertex and edge a constant number of times, plus work proportional to building or scanning reversed edges. Space is order v for visited flags and the finish order, and often order v plus e if you store the transpose graph explicitly. Tarjan's algorithm also runs in order v plus e time with a single depth-first search. Space is order v for discovery and low-link values, the vertex stack, and bookkeeping for which vertices are still on the stack. Kosaraju pseudocode, first pass depth-first search on the original graph records finish order. Second pass on the transposed graph, processing vertices in reverse finish order, collects each strongly connected component. Tarjan pseudocode, one depth-first search assigns discovery and low-link values, keeps a stack, and whenever low equals discovery at a vertex, pops one strongly connected component.